Okay, thank you so much. So our next speaker is Tshidiso Mazibuko and Katherine Malan, presenting on machine learning for improved boiler control in the power generation industry.
Okay, thank you very much. Good afternoon, everyone. Let me share my screen. Okay, can everyone see my screen?
Yes, we can.
Okay, and am I audible enough?
Yes, we're good to go.
Okay, thank you once again. As introduced, I'm Tshidiso Mazibuko. I'm an MSc student at UNISA, and my supervisor is Professor K. Malan. And the title of our paper is Machine Learning for Improved Boiler Control in the Power Generation Industry. So power generation plants in South Africa experience two major problems. One of low availability, and the second one of low combustion efficiency. According to the CSR study conducted in 2018, the availability of Eskom steam boilers was around 67% at that time, which is quite a very low figure. And this low availability, which is caused by failure of steam boilers, caused a decline in the South African GDP of between 59 billion and 120 billion in 2019. So that's according to the CSR study. And as you know, in South Africa, this is commonly known as load shedding. Okay, so this is the cost of load shedding to the South African economy in 2019. And a separate study was conducted in South Africa of what are the main causes of failures in steam boilers. Okay, so the first one is overheating, which accounts for close to 60% of failures. The second one is corrosion or erosion, which accounts for 23% of failures. And then you have fatigue and stress corrosion cracking. And what is the problem with overheating? Okay, overheating leads to tube leaks, or what is commonly known as pipe leaks. And this eventually leads to unplanned shutdowns. Probably if you have had Eskom representatives giving explanation of what the causes of load shedding are, one of the causes is pipe leaks in steam boilers. Okay. And the second problem of low combustion efficiency, what is the problem is that if you have low combustion efficiency, you spend more money for the fuel for the same amount of steam that you want to produce. And if you spend more money for the fuel that you use for steam combustion, you increase the input cost of your fuel. So in our case, the fuel that we use mainly is coal. And our study was divided into two. So we firstly started with literature review on the use of machine learning models in improving combustion efficiency and availability of steam boilers. And the second part of our study is that then we extended one of these case studies with the aim to improve the accuracy and or reduce the complexity of the machine learning models. And the reason behind this is that if you want to use machine learning models in industry for practical application, Ideally, you would want to have a machine learning model that is fairly accurate, but that is less complex, and that is less computationally expensive. Otherwise, you just have a fancy model that would be a nice to have. And generally, such models are not implemented in industry for practical reasons, as I've said. If they are computationally expensive, they will not be utilized at all. Okay, before we go any further, what is a steam boiler? A steam boiler in a power generation plant simply produces steam. Okay, and does so by exchanging heat released from burning a fuel source. In our case, the fuel source is coal, but you can have natural gas. And coming to think about it, okay, in Kuba, our nuclear power plant in Cape Town uses nuclear as a fuel source. And it exchanges heat released from burning a fuel source with boiler feed water, and that's how you produce steam. Okay, and just to give you a schematic diagram of what the steam boiler looks like. This is what you have. You have coal here with a mixture of air, hot air, being combusted. And these yellow flames here represent combustion zones. And the energy released from combusting this coal is exchanged with water flowing inside the water wall tubes, these blue lines here. Okay, and inside this water wall tubes, you form a mixture of steam and water. Steam is separated in a steam drum, and the steam is further heated by the flue gas, which is a byproduct of combustion. It is further heated to form superheated steam. And this superheated steam is then directed to a turbine, which essentially turns a turbine and you produce electricity. And your flue gas gets sucked up normally by a fan, and it gets emitted to the atmosphere. Okay, so this is simply a simple representation of what a steam generator looks like. Okay, so let's go to the first part of our study, which was to look at the four cases, 4 case studies. We simply picked 4 case studies that were of interest to us, that used machine learning to solve problems related to availability and combustion efficiency. So the first one is a biosteam boiler root cause analysis. So this was a South African based study for a biomass steam boiler. And essentially, it used machine learning models to determine the root causes of high superheated steam temperature. And this high superheated steam temperature can cause problems when it comes to superheated tube leaks or pipe leaks. And it can cause downstream equipment failure, like your turbine, for example. And through the use of this machine learning model with sensitivity analysis, they determined that a combination of 3 variables out of 28 variables, and those 3 variables will be your fuel mixture content, fuel moisture content, high fuel density, and your high draft fan damper position, were essentially the cause of this high superheated steam temperature, which is around 40% above the design limit. Okay, so there could have been other tools that could be used, like computational fluid dynamics, But as we know, computational fluid dynamics, it's very computationally expensive, and it requires expertise when it comes to its usage. And machine learning models in this regard, they provide a good turnaround time when it comes to providing solutions. The second study was on the steam boiler pipe leak detection system. Also, this was on a steam boiler in Poland, like 600 megawatt steam boiler in Poland, which is equivalent to one of our, in terms of generation, power generation is equivalent to one of our steam boilers in South Africa. So in this case, they used principal component analysis to detect pipe leaks in steam boilers. And they applied this for 25 cases of shutdowns, And the PCA could actually detect pipe leaks 5 days ahead of the shutdown or just before the shutdown. And the implication of this is that if you can predict a pipe leak way ahead of an emergency shutdown, is that you minimize the severity of failure and you minimize the cost of maintenance. Okay. For a very simple reason, you detect the problem in its early stages, and you're not going to spend more money in maintenance to repair your pipes. And the third one was on steam boiler combustion efficiency. And in this case study, they used the K-means clustering to create clusters of moves of operations. And they would actually have efficiency levels for each of the data points. And for a future data point, what they would do is then they would determine the control settings of a boiler with a higher combustion efficiency level. So within each cluster, if a future data point, let's say, falls within a certain cluster, let's say cluster A, and then it will search, they would have a search algorithm where they essentially searches for a control setting that will give you a higher combustion efficiency. And they would use another machine learning model, a predictive machine learning model, as a visual tool to test if the control settings predicted an increase in efficiency level. Okay, and essentially, the machine learning model that they used as a visual tool could predict an increase in efficiency level. And as I've said previously, an increased efficiency level leads to lower input cost of your fuel. And that fuel can be coal, can be nuclear, can be a nuclear fuel, or can be natural gas. And the fourth study was on optimizing boiler control in real time using machine learning. And this is the case study that we took for further analysis. So in contrast to the second case study, which was detecting pipe leaks, in this one, we are trying to prevent the cause of pipe leaks. So essentially what they used here is that they used a machine learning algorithm to predict temperature zones of 6 combustion zones and oxygen content of your flow system. And then they would use the two machine learning models, one for temperature prediction and the other for prediction of oxygen content, as constraints in the optimization model. And the aim of the optimization model is to maintain uniform temperature across the combustion zones. So, and by doing that, you are actually avoiding overheating, which eventually leads to pipe leaks. And the uniform and low oxygen concentration of the fluid actually leads to, it's an indirect measure of your combustion efficiency. So the lower the oxygen concentration of your fluid system, the better your combustion efficiency. Yeah. And yes,
Tshidiso,
yes,
just a quick heads up, your time is actually up right now, but there's 6 more minutes in the session. So maybe if you can tell us the pertinent findings or methodologies.
okay, yes.
There's 6 minutes.
Okay, no, that's fine. Okay. So if I just have to move, this is the motivation around the study, is to use your oxygen prediction and temperature prediction machine learning models as part of your constraints here. And what the optimization model actually solves for controllable variables that will actually be used to control the distributed control system. So it's using a machine learning model and optimization model in real time. And if you want to use optimization model in real time, the focus should also be on the speed and the accuracy of these two machine learning models. And the aim of our study was just to determine what the impact of reducing the number of features will be on the accuracy of the machine model. Okay, so it's to improve computational cost and so forth. And to do that, we essentially applied sequential feature selection on steady-state input data, and we compared our results to that of Ding and his associates. Okay, and this was just the general data set. And yes, and because we're using steady-state data, we performed hyperparameter optimization for each of the combustion zones. And then we perform feature selection for each of the combustion zones, and then we could make predictions on the selected features, and we compared our results to that of Dean. And just a quick background, and this is our results. You can see that on the average, we used two metrics actually to compare our results. For the first part of 34 features, okay, with steady state, Ding's original results showed a mean squared error of 1,860. And the second column is simply mean average percentage error. And he applied the time series data on the input data, and that actually improved the MSC from 1,860 to 247. And in our case, we took the steady-state data with feature selection, that improved our results from 1,860 to 326, just by performing feature selection. And in conclusion, what can we conclude is that indeed we can use machine learning to solve problems of availability and combustion efficiency. And sequential feature selection can be used to improve the accuracy of the support vector regression model using steady-state input data. And this helps with future training, because you'll have a less complex machine learning model. And then that machine learning model will be computationally less expensive. Thank you very much. If you have any questions, you can pose those questions to me.
Thank you so much for that presentation. It was very informative. I have a question on your data set.